Okay, ni topik kita hari ini. Alright, today we are going to talk about application in linear and angular kinetics. Okay, kita cerita tentang kinetics, or we are going to talk about the action of force. Alright, if we take a look at what we have learned before, okay, yang itu kita dah bincang separuh topik ni sebenarnya. This one. Ni, work, power and energy. Okay, and then I think that's all. Ni, impulse and momentum. Because impulse and momentum is actually part of linear kinetics and also work, power and energy. So those two had already explained about the first part of our chapter, but we are going to uh, discuss it a bit. Yang kita punya main for today is actually the second part of our apa ni? The second part of our topic, which is regarding angular kinetics. Jadi kita akan tengok sama macam topik kinematics. We are going to see what are the similarities in term of formula, in term of usage between linear and angular kinematics. So linear kinematics, we have learned about impulse momentum. Same goes as angular kinetics. We are going to see angular impulse, angular momentum, and also other form of properties in the angular kinetics. Okay, tu yang kita akan buat hari ni lah. Right, so let's go. This one still the introduction of it. What is kinetics? As kinematic is pattern, so kinetic is the cause of that pattern. Okay, kinematic to pattern, kinetic is the cause of that pattern. In other words, kinetic is force. We talk about force. We talk about the different type or different function of force, different use of force, different properties of force. Force tu satu benda, F. Okay, now we are going to talk about force in different shapes, such as impulse, Ft, such as momentum, Mv. Okay, so all of that we are going to discuss again in terms of angular. Right, so that is kinetic. And then what is a force? When we talk about force, force is actually an action, whether it is a push action or a pull action. And when we talk about force, it can be characterized by magnitude. Magnitude is how much? Berapa Newton atau magnitude. Direction of application from where to where. Is it positive? Is it negative? If from left to right, positive. If from right to left, negative. If from bottom up, positive. From top to bottom, negative. Atau masuk direction. And finally, is point of application, where it being pointed at the object. Okay, because when we talk about force, okay, when we point force to stop gak sebenarnya ni. Okay, when we point force to an object, it will actually work in two different ways. Okay, contoh bila kita ada satu objek, point of application. This point of application is important because when we talk about force, whenever you push an object, there will always be a resistance. Okay, known as this one is force application force, this one is kinetic force, ataupun nama kampung dia, it will be known as friction. Ni benda ni. Okay, and that is the reason why we need to know point of application, because friction always works in vice versa. If the point of application is from bottom up, so the friction is going to be from top to bottom. Air friction. So kita kena tahu dia punya point of application. Ni masih intro Okay. And then when we talk about force, it can be from two different sources. The first one is known as internal force. Paling senang nak ingat internal force, muscle contraction. Okay, force that being produced inside your body. And the external force is actually a force that being delivered ataupun a contact force. Kita boleh panggil external sebagai delivered or contact force. Benda bersentuhan means the force being transferred from one to another. That is external force, such as collision, external force, such as kicking the ball, that impulse, external force, because the ball does not have force. The force being produced at the leak. So force produced internally and being transferred to the ball. That is external force. Okay, this is the two type of forces. Alright, and then we have this 3 Newton law. Newton law ni kita dah cover kan? Does we cover this one? Dah. Okay, Newton first law, second law, third law. Where first law is about no force, no movement. Second law is about when you inflict force, there will be movement. So the properties of the movement. And the third law talks about if you try to gain more outcome, you need to actually invest more force. Okay, what you give, you get back. All right. And then we have torque. Okay, torque is also a type of force where the force being produced or being delivered to an object from two different sides, which cause a rotational action. Ni force satu, force dua. Multiple force being proposed to an object from different direction. This one is known as torque. Okay, so in human body, kita mungkin tak nampak force dua macam ni ya, tapi let's see our hand column. So the bicep work this way and the weight that we held work that way. So weight is also a form of force. And when you have two different kind of force works in different direction, you are going to get a rotational lah. Jadi action macam ni, if F, kita namakan F bicep lah. F bicep dengan F weight. If FB is larger than FW, you are going to get a contraction. If FW is larger than FB, you are going to get a retraction. Either way, this is a rotation because that movement happen to be at the axis of rotation. Ini maksud torque. Okay, putaran yang dihasilkan oleh two different force acted from two different direction. Okay, to measure force, we have two type of measurement. One is known as direct measurement. Second one is known as indirect measurement. So most of the time, if you have the facilities, we are going to rely on direct measurement. Like what we have in the lab. So kita ada force plate. Okay, kita ada force plate. Kalau kita tak ada semua benda ni, yes, we can measuring force. Indirectly means prediction. So based on equation. Kalau based on equation ni, sometimes the result is going to be exact. But sometimes it is not, since we predict. Okay, we predict based on our mass, based on the acceleration. If the measurement of the mass is not correct, so the measurement of the force is not going to be correct. Same goes as if the measurement of acceleration is not exact. Jadi pasal tu nama dia indirect lah. Kalau direct measurement, you stand on the force plate, they are going to measure. You jump on the force plate, they are going to measure based on the transducers that we put inside the force plate. Okay, and most of the time the sensitivity is up until to 0.001%. It is dead accurate lah, senang cakap, if you calibrate the item regularly. Okay, that is measuring how we measure force. Okay, this is a free body diagram. This one is to explain about projectile. I think that one also, we also have covered that projectile. Okay, free body diagram. So we are going to skip this one. Okay, ini adalah beberapa jenis lain free body diagram based on situation. Okay, again, when we talk about free body diagram, you need to remember you have these three. Okay, air resistance, external force, and gravity. Jadi bila kamu masuk dekat gambar macam mana pun, always downwards is gravity. Ingat yang tu dulu. Always downward is gravity. And then to the left or to the right, you are going to have force and resistance. Okay, force and resistance. And to the top, you are going to get depends. It depends. Okay, kalau macam yang ini, kita ada apa kat atas? Normal force, nothing. Okay, this is nothing. Tapi bila kita masuk yang ini, kita ada FF, friction force. Why? Because this box is moving downwards. Kalau yang ini FF dia, tengok mana dia bergerak. Okay, FF ni tengok mana dia bergerak. Friction or air resistance. Okay, tengok di mana. Okay, kalau macam ni, kenapa dia tak ada FF? Why free fall does not have friction? Dia ada friction ke tak ada kat sini? Hello. Hi. Assalamualaikum. Anybody home?
Tak ada.
Kenapa dia tak ada friction?
Dia tak bergising dengan apa-apa.
Dia tak bergising dengan apa-apa. Okay. Yang ini kenapa atas dia tension? Why put here tension? T instead of other things. Instead of force or whatsoever. Kenapa dia boleh bagi tahu sini atas ni adalah tension?
Sebab dia hanging kan.
Sebab dia hanging. Okay, sebab dia hanging. So there are force being subjected to this hanging action. So that is tension. Other than that, kalau ke atas, okay, kalau ke atas kamu kena tengok. Selalunya dia adalah normal force. Okay, normal force means the force that being subjected. Berat benda ni. Okay, selalunya berat benda ni, Fn. Okay, W ni weight ni, it try to show you this berat with gravity. And then only you are going to get weight. Okay, tu weight. Lain pada tu, force lah. Force applied. Okay, tengok dia bergerak ke mana force applied. So lawan dia will be friction. Ni free body diagram which only subjected to force, external force, friction or air resistance and also gravitational force. Ni dia nak cerita force apa yang ada pada sesuatu objek. Okay, and then we have vector algebra. This should be covered during your diploma level. Okay, vector algebra ni dia nak tunjukkan numbers but in term of drawings. Okay, all of this is representing force. Amount of force, the length of the arrow is the magnitude of the force. The what we call it, the direction of the arrows is the direction of the force being applied. Ni vector algebra. Jadi dia ada berbagai-bagai lah. Contoh macam if we compare this kind of arrow dengan arrow yang lebih panjang, so the longer the arrow, the more magnitude of the force you have. Okay. Jadi kalau kata kita buat penambahan vektor, what we are going to do is if the direction is similar, you are going to measure how long. Kalau ni kata 2 cm, ni 4 cm, means the answer will be 6 cm. Dia tambah je. But if the direction is not in the equal direction, the direction is not equal. So what we are going to do is from apa ni? Kita panggil dia daripada tail to head. Okay, tail to head. Jadi kita akan ambil dulu yang pertama. Let's say this one is 2 cm. 2 cm. And then yang ni 3 cm. Kita akan sambung. Thus 3 cm. Jadi hasil dia, the hasil is not this two, but the hasil is going to be the resultant. Tail to head. Jadi kita akan ambil tail to head. This is the resultant. Yang ini yang kita perlukan. Ini vector algebra. Okay, kalau kata kalau kita ada satu macam ni, campur dengan satu macam ni. Okay, hasil dia. So, you are going to get satu, you are going to get dua. And then, tail to head. This is the resultant. Meaning that, if we add on the first force with the second force, the object will actually move as the third line. Bola tu akan bergerak macam tu kalau kita bagi force macam ni. Kalau kita bagi force menegak, lepas tu ke atas, we give these two force. Result is you're going to get something like this. Bola tu akan go diagonally upwards. Ni vector algebra. Okay, so the tip is tail to head. Okay, kalau kata kita ada pukulan pertama, force pertama is this one, campur dengan force kedua, this one. So hasil dia, we are going to see the first one, we are going to see the second one, and tail to head. Means the object is going to move downwards macam tu. Ini hasil dia. This is what we call vector algebra. Okay, you need to measure the length, and then at the end kita akan dapat hasil dia resultant. Kalau kata both of the vector is at the same direction, and then it's going to get similar. Kalau ni 2 cm, 2 cm, the result will be 4 cm in the same direction. But if the direction is not similar, so the way for you to find out the resultant is by consulting tail to head. Okay, satu ke bawah, kalau kata ni 4 cm, So this is going to be 4. Kalau kata ni 2 cm. So this is going to be 2. Jadi hasil dia tail to head. Ni hasil resultant dia. So this is what we call as vector algebra. Okay, ni vector algebra. Okay, kalau kata sama pula, sama arah. Cuma, sama bentuk but different direction. Kita kena ukur. Let's say this one is 1 cm, this one is 2 cm. Siapa lagi banyak? So yang hasil dia akan follow direction yang lebih banyak. Okay. Ni yang last tadi lah. So we go tail to head. Okay, tip to tail lah. Tip to tail. Dia panggil tip to tail. Senang kita ambil tail to head. Tail yang ujung. Macam dia ambil daripada atas, dia tarik bawah. Okay dia macam tu. Okay. Macam yang ni dia kata tip to tail ni. So dia ambil daripada puncak, dia tarik ke bawah. So ending dia tetap sama. Tip daripada ekor yang ada ke puncak yang ada. So that will be tail to head. This one is the resultant. Result dia macam ni. Okay, so ada 3 jenis lah. Satu, where you have similar direction. Okay, just add on the length. Dua, similar direction but have positive and negative. So it depends. Okay, it depends. The direction is based on whichever had the most magnitude. But if the vector is totally different in term direction, so you are going to based on here, you are going to make a line on start on the tip and end on the tail. Okay, ni tip to tail lah. Saya selalu sebut tail to head. Sama je mana-mana. Okay, from one tail to one head, or from one head to one tail lah. Dia panggil from one tip to one tail lah. Tip to tail. So mana-mana lah kamu dapat, kamu ingat yang mana-mana tu lah. Yang itulah. Okay. Tapi untuk sambung dia, dia kena follow benda tu. Kamu tak boleh sambung ikut suka. Macam ni kan ada 3 kan. Nak buat ni dulu, lepas tu nak buat yang ni tak boleh. So kita kena ikut. The first one, okay, tail to head. And then the second one, from the head, bawa ke lagi satu. And then the third one, from the head, bawa lagi satu. Ni kan dia mula satu. And then the second one, this one. Okay, and then the third one. So daripada head yang ketiga tu. And then untuk resultant, tail to head. Tail yang ada dengan head yang ada. So that is the resultant. Meaning if we apply these 3 force to an object, the force is going to actually move like this. The resultant. Ni vector algebra lah. Okay, or we call it as vector resultant resolution. Operation that replace a single vector with 2 perpendicular vector such that the vector composition of the 2 perpendicular vector yield the original vector. Itulah dia. Okay, untuk kita hasilkan apa ni? Untuk kita hasilkan ni. Okay, ini kan, okay, take a good look here. This one dengan this one. Ini macam nak cakap this is quite like theorem Pythagoras. Okay, theorem Pythagoras. Okay, the difference between this. Oh, ada siapa bertanya ke? Hanif. Any question, Hanif? Hanif, Muzaffar, ada soalan?
Saya tak ada, sir.
Dah tu kau angkat tangan?
Tertekan, sir. Tertekan.
Okay. Alright. If we take a look here, dengan yang ini, tengok betul-betul apa beza dia. This one is vector composition. Vector resolution. Okay, this is vector resolution. This is vector composition. Okay, beza dia, this one, when we try to compose the vector, we are going to add on all the vector. Means we are going to get only one direction of force at the end of the day. Vector composition. Macam ni bila kamu nampak vector composition, means kamu kena tambah. When you see vector resolution, okay, resolution is operation that replace a single vector with 2 perpendicular vectors such that the vector composition of the 2 perpendicular vector yields the original vector. Okay, vector resolution, if you take a look closely, dia bukan penambahan vektor, but we change the directional of the vector. Kadang-kadang orang confuse tengok arah vektor ni. Satu vektor vertikal dia ke atas, satu vektor horizontal dia ke kanan. Okay, ke atas dan ke kanan. Kalau kita buat vector composition, it is not going to be resolution. Vector composition macam ni. Kalau kita ada satu macam ni, plus dengan satu macam ni. What we are going to do is we are going to do the first one and we are going to do the second one. And tail to hit. Hit to tail. This is the resultant. Vector resolution, kalau kita ada force macam ni, we try to resolute dia, apa yang akan terjadi ialah 1, 2. Jadi resolution dia, kita kena tengok yang mana lagi besar. Katalah ini 4 cm, ini 2 cm, jadi line kita dia akan lebih vertical. So this will be the resultant. And this is actually just, what we call it, a representation of the vector. Just a representation. At the end of the day, to solve this one, we are going to do calculation based on this. Kita akan pakai either sin atau cos. Ini untuk kita selesaikan vektor. Okay, ni apa ni orang kata? Revision. Okay, this is just a revision. Okay. Now we go to our main gist for today. Okay, our main gist for today. Alright. Okay, we have several properties to be discussed. Kita tengok dulu. The first one is centripetal force. And after centripetal force, we are going to talk about moment of inertia. Okay. And then we are going to talk about angular momentum. And finally, it is regarding angular impulse. Okay. Last kali kita ada talk. Okay. So before we go further, these are the equivalent between all those linear quantities with what we call it angular quantities. Contoh macam mass. Kita ada mass dekat dalam linear where we measure it in term of kg. So in angular, mass is going to be known as moment of inertia. Okay, moment of inertia. Benda yang sama like we have discussed on kinematics, where we include radius. Same goes here. Okay. Jadi mass linearly, angular, we call it as moment of inertia, where it is actually mass times the radius. Okay. Kejap lagi kita datang confuse kejap lagi. Kenapa K kejap-kejap K kejap-kejap R? R is radius, K also radius. The difference is R is radius of rotation, while K is radius of gyration. Okay, satu rotation, satu gyration. Sometimes it is similar, sometimes it is not. Kita tengok nanti. Okay, and then we have force. Force yang ada dekat linear tu, where we measure it in term of Newton, in angular it is known as torque. Ni benda kita dah belajar. F dengan distance. Distance of what? Distance between the force application and the axis of rotation. Ni contohlah. Kita ada lengan. So we have axis here. We have force. Okay. Jadi kita nak tahu berapa dia punya torque. Mana radius? Radius is between these. Axis of rotation perpendicular to the line of force, the distance. So these are radius ataupun D. Ni T equals to F D. These are the D. Okay. Okay, kalau kata kita ada case buku lah, buku. Kita tolak dia. Kita nak tahu berapa radius dia. We need to draw line of force application and then a perpendicular line intersect with the axis. So between the range between the line of force application and the axis of rotation, this is dia punya D ataupun dia punya R. It is a line, it is the distance perpendicular from the force to the axis of rotation. Kalau macam yang ni senang lah kita nampak pasal axis rotation dia selari dengan force. But when we put a force skewed from the axis of rotation, this is how you find out dia punya D. Okay, untuk cari torque. Alright. And then we have momentum. Ni impulse and momentum theorem. Okay. So if we have something like this, I equals to M, where Ft equals to mv, okay, impulse momentum theorem, linearly, same goes as angular. So dalam angular momentum, we name it as H. Impulse, Tt. Jadi dia sama. Okay, Tt. Okay, ni mana dia tak tulis simbol dia. Dia Tt. Okay, so kalau angular momentum, it is mk square omega. Tt dia ialah Fd. Is it? Fd. Okay, benda yang sama. Sama dengan ini. This one is angular momentum. This one is angular impulse. Okay, mk square omega. Alright, these are the formula, the translation of formula between linear and kinematics. Now let's go back and let's see the properties of angular one by one. Okay, so we are going to start with centripetal force. Okay, what is centripetal force? Centripetal force is actually a linear force. Ingat balik masa kita belajar angular acceleration. Do we have covered that one? Angular, yes, angular kinematics. Angular acceleration. Okay, sorry. In angular acceleration, kita ada dua. Satu, acceleration at the surface, where we call it as tangent acceleration. Satu lagi, kawan dia from the surface inwards, where we call it as radial acceleration. Still remember this one? Ke dah tak ingat dah? Ni beberapa minggu lepas kot. Do you still remember this one?
Yes.
Yes. Okay. So, tangent acceleration and radial acceleration is actually a linear acceleration. But by combining these two acceleration, we actually happen to able to control the shape of the rotation. Means we can have this kind of shape, we can have a very perfect shape, maybe we can have something yang go up, down, where at here, ni kan yang paling jauh ni, the acceleration is like that. Okay, jadi dia akan counter if the round shape is perfectly sphere, so the figures of the acceleration between AT and AR is equal. Jadi centripetal force is a force that play a major role in this one. A force that being directed toward the center of rotation. Means if this force is large enough, it will pull the rotation inwards. But if the force is lacking, you are going to get skewed curve. Okay. Jadi contoh macam kita tengok orang buat lontar tukul besi. So in order to sustain the weight of the what we call it, hammer, okay, of the hammer, an enormous centripetal force will be put inside in order to ensure that orang tu rotate cantik. Kalau dia tak ada centripetal force yang kuat, what is going to happen is when he rotate, dia akan terikut hammer tu keluar. So the rotation is not going to be perfect. The rotation is going to be jagged. Kejap bulat, kejap lonjong, kejap bulat, kejap lonjong. Same goes as tangent and radial acceleration. Okay, so force directed towards the center of rotation for a body in rotational motion. Okay, so formula dia ni beralih. Okay, we can write it out as force centripetal equals to mr square v, mr pula, mv square r, mv square r, ataupun force centripetal is mr square mr omega square. Okay, where M is the mass. Oh, sorry. M is the mass. R is the radius. And these two, it depends. If the information being given in terms of angular velocity, and then you are going to consult this equation. But if the information being given in terms of linear velocity, you are going to consult the top one. So either one, sama je. Okay, either one, dia sama saja. Kat sini. Okay, ni macam centripetal force. Sekejap, saya tengok contoh dia tak. Centripetal force. Centripetal FC. Sekejap Okay. Hit with centripetal forces. Sling. Right. So, let's go to the first example. Kita ada seorang, kita ambil case tadi. Okay, jadi dia swing. Hammer swing. Ni hammer. Hammer berputar. Okay, let's see the length of this system, hand and chain, is 0.75 meter. Okay. An athlete swing a 0.75 meter sling of negligible weight around her head with a centripetal force of 220. So there are force acted to the axis, which noted to be 220 Newton. Okay. And the Right. So the question is, what is the initial velocity of the object? Okay, of the object if the weight of the head is weight 9 Newton. Kita nak tahu berapa laju putaran yang akan dihasilkan of this person where 220 Newton of centripetal force being subjected to the system and the weight of the system is 9 Newton. So how fast? Bila dia tanya macam ni, how fast? So we know that we try to find out V. Jadi kita pakai equation yang pertama, which is centripetal force equals to mv square over r. So dia tanya dia tanya putaran. Betul, dia tanya velocity dia. So dia bukan tanya angular velocity. Kalau dia tanya angular velocity of rotation or whatsoever, lain cerita. Sekarang dia tanya putaran ini berapa laju. So we are going to use the first equation to find out the answer. Cuba jawapan ni. Cuba jawab. 220 equals to 0.75 p square over silap, sorry. It will be 9 over 9.81. Pasal berat ni dia bagi dalam Newton. This one is mass. So mass is weight divided with gravity. So weight is 9 Newton, the gravity is 9.81, and the R is 0.75. So we switch side. We have 9 over 9.81 V square equals to 220 times 0.75. So V is 220 times 0.75 divide 9 over 9.81 square root. Berapa jawapannya bawah? 220 kali 0.75 165. 9 bagi 9.81. 0.92.
13.4 meter per second.
13.4
Meter per second.
meter per second. Yes, that is correct. 13.4 meter per second. Ni penggunaan dia lah. Salah satu penggunaan dia. Okay. Let's try second one. Okay. Yang ni semua okay? Dapat? Dapat, saya nak pergi page sebelah. Ui, Paul. Sikit.
Dapat sir, dapat.
Okay.
Dapat saya.
Kita kita ada hammer. We have a hammer. Again, kita ada hammer. Hammer Thor pula. Thor. Benda nama hammer Thor tu dia nama kan? Siapa-siapa tengok Avengers, apa nama binatang ni?
Ada.
Apa nama dia?
Jonathan.
Jadah. Okay, hammer ni datang the weight of this hammer is 7.27 kg. Okay, nampak kg, weight. Ni weight pula, mass. When you see kg, this is mass. Kalau weight, dia mesti dalam Newton. Okay, on a 1 meter wire. Okay, so dia ada, kita assume dia ni lah. Kita assume tangkai dia ni, radius dia 1 meter. Okay, it being released with a linear velocity. So after it being rotate, and then the athlete release the hammer, and the hammer travel at 28 meter per second. Okay, what reaction force is exerted on the thrower by the hammer at the instant before the release? Ambil kau apa benda soalan. Soalan dia mudah je. What is the reaction force exerted, okay, by the thrower? In other words, they try to find out how much F being exerted by thrower. Jadi apa maklumat yang kita ada? We have mass, we have velocity, we have radius. So we go to the second equation tu. To the first equation lah. mv square over r. Tak payah nak sakit kepala pergi cari omega pula kat sini. Okay. Soalan dia, tengok betul-betul what reaction force is exerted? What reaction force is exerted? So we know that in a throwing action, there are centripetal force moving inwards. Kalau orang ni pegang kat sini, at the same time orang ni akan exert Newton's third law. Okay. So there will be force equal and opposite. In other words, you find the centripetal force, you know the amount of force being exerted by the thrower. Pakai formula yang sama. Okay. So mass dia berapa? 7.27. Velocity dia berapa? 28 square. Okay, lagi apa kita ada? Radius dia berapa? Punat. 28 square kali dengan 7.27. Berapa? Oh, ambil kau. 5,699 Newton. 5,996 Newton. Ini jawapan ni. Okay, this is the answer. Or if you think the answer is too much, tukarlah dia kepada 5.9 kilo Newton. Pun boleh. Means that the centripetal force acted upon the system is 5.9 kilonewton. This is quite high. In order to ensure the hammer able to travel at 28 meter per second, or else it's going to travel slower. Ataupun mungkin tak travel, dia jagged. Okay, that is centripetal force, means the force that acted upon the system. So if the force acted upon the system, in other words, there also force being delivered by the athletes. Inilah yang dia ni tanya tadi, what is the force being exerted or being delivered by the athlete? It will be equal with the force that being exerted in term of centripetal. Jadi apa yang kamu dapat tangkap tentang centripetal force ni? What are the difference between force and centripetal force? What are the difference? Apa enggak difference-nya? Cubalah seorang. Jangan risau. Kalau salah, repeat. What are the difference between force and centripetal force? Or maybe you see the similarities. What are the similarities between these two properties? Those are force. Those two are force. Tapi satu nama force, satu nama centripetal force. Apa beza dia? What are the difference or similarities? Dapat tak? Dapat tangkap tak?
Direction dia, sir.
Direction. Satu direction keluar, satu direction ke dalam. Lagi? Kalau kita cerita force kan, kita ada kotak. Ni force, betul kan? Betul tak? Kalau kita cerita force, in order for us to move this box, these are the force that will be inflicted. But in angular, the force is still quite linear. Okay? Cuma, okay, except that centripetal force is the force that ensure the rotation occurs. Maksudnya, centripetal force ni adalah force yang kita inflict kepada sesuatu rotation. Okay? Single direction. If two direction, torque. Single direction, it will be centripetal force. And this force keep rotation to be present. Kalau linear force, tak akan ada rotation present because it is linearly, tegak je. But centripetal force is the force that actually bring the rotation to be that kind of rotation. So kalau centripetal force tak ada, dia tak boleh jadi benda ni. Means when we try to swing hammer kan, tapi centripetal force tak ada, dia tak akan jadi macam ni. Instead dia akan jadi macam ni. Dia akan jadi linear. Tu beza centripetal force dengan linear force. Those two is actually force. Okay, it is actually force, but the application is different. It cause a rotation, centripetal. It cause a translation, linear force. Itu adalah properties yang pertama. Centripetal force. Force that being directed towards the center of rotation for the body in rotational motion. Contoh dia lah. Okay, physics play a great deal in the design and technique of driving a racing car. Why a Formula One race car flat and have such a wide wheelbase? Wide wheelbase. Okay, it is because the wider the car, the faster it corner. Okay. Ni contoh. Jadi bila dia corner macam ni, centripetal force dia ke mana? Ni Mamat ni tengah ambil corner left hand side. So centripetal dia ke arah left ke arah right. And what happen if there are no centripetal force? Okay, try. Force dia ke sini ke ni, ke kanan ni, ke dalam okay, ke dalam ataupun keluar. First, I need to know what is the direction of the centripetal force in this action. Inwards, outwards. Ke mana dulu?
Ke dalam ke?
Ke dalam ke dalam. Cik. Ke dalam. What happen if the centripetal force is not enough? Apa jadi? Kalau centripetal force tidak cukup. Pernah tak kamu drive kereta, okay, you drive your car quite fast and take a lap and you notice that your car tire does not grip the road and you start skidding out. Kik keluar. Pernah tak rasa begitu? Kalau tak pernah, hidup korang tak cukup menarik gini.
Pernah.
Nah, sir. Terlajak.
Bukan terlajak, dia bukan terlajak, okay? Dia bukan terlajak, dia bukan drifting, but this is actually understeer. Tayar belakang lari ke tepi. Okay, that happen when centripetal force is not enough between you to the center of the axis of the rotation. Sometimes it is not due to your car, but it is due to your rotation. Okay, kamu cuba untuk rotate terlalu cepat. Daripada tegak jadi lap terlalu cepat. The angle is too steep, resulting not enough centripetal force. Means you are not going to get the lap. You are going to overshoot. To overshooting is the effect of lacking in terms of centripetal force. Tak cukup. Okay. So when the car approach a corner without some force applied, the car would continue on a straight line. Okay. Macam mana kita nak tengok ayat pertama ni, macam mana kita nak bagi force? How we want to apply force to a curve. Kita nak ambil lap. Okay. Kita nak ambil lap ni. Okay. Dia kata, you need to apply force. So how you want to apply, this is, let's say this is your car. How you want to apply force so that you may have something like this instead of something like this. With force. Without force. How you want to be here and not there. How you want to apply force. Macam mana? Macam mana kita nak apply force dekat sini? Kalau orang, kita bolehlah sepak terajang kan. Ni sekarang kita tengah bawa kereta. We need to apply ample and correct timing of force in order to not go to the left hand side. Instead, take the curve. How we want to do that? Siapa-siapa nak try? Siapa-siapa yang pernah skidding tadi mungkin boleh bagi jawapan kot. For sure, after second and third try, you are not skidding anymore. Macam mana? Ni konsep centripetal force. Means, if we have enough force inwards, this is FC. Okay, this is the axis. If we have enough FC, kita akan dapat curve ni. But if we don't have enough FC, we are going to go there. For sure. So now, when we talk about FC, it is mv square over r. Apa yang kita boleh ubah kat sini? Macam mana kita nak naikkan FC? Just play around with this. Can we change the weight of the car? Boleh tak kita change weight kereta? Ni kena fikir betul-betul. How we want to ensure our centripetal force is enough. Macam mana? So, dia punya tricks ada dengan benda ni. Ataupun, dia ada dengan benda ni. MR omega square. The thing that change here is only one. Okay, now let's take a look. The force must produce a change in direction towards the center of the curve. The type of force that acts perpendicular to the car velocity is called centripetal force. Centripetal force means center seeking. It acts to change the direction of the car, but not the speed. So how you actually change the force? Okay, so here, the one that need to be changed is the center of the gravity, the mass of the car. Nanti kejap lagi kita sampai dekat moment of inertia, kamu akan faham. Okay, in rotation, let's say we have something like this. We have something rotate. Kita ambil wake. And then we have something rotate. The same axis. Tapi apa yang berbeza antara A dengan B? What is the difference between A and B? Dia punya radius. Okay. When we change or when we reduce the radius of rotation in angular motion, weight is going to be less. When we increase the radius of rotation in angular motion, the weight is going to be heavier or more enormous. So let's watch this video to further understand weight distribution in angular motion.
It's a very low friction rotating platform. What I'm going to do is I'm going to stand on that platform. I'm going to hold these weights out. When I hold these weights out like this, I'm going to spin like this. When I hold them out far, do I have a lot of rotational inertia or a little? How about when I pull them in? A little? So if I get here rotating like this, and I hold them out, what happens when I pull them in? Ooh. Easier to rotate, gang. Harder to rotate. Easier to rotate. Harder. Woo! Woo! Okay. You see such thing? All right? All right? You go to the... Ooh, little kiss it is. You go to the ice volleys, you see the skaters turning around.
Okay, dapat tangkap? Do you get the idea? Dah diam balik. Hello, korang ada ke kat situ? Are you there?
Ada saya ada.
Ada, okay. Ni lagi satu contoh.
Dia saya ada.
Okay, ni week being distributed out.
1, 2, 3.
Siapa yang ada playground tu nak ada benda ni nak try ajak kawan-kawan. Okay, when the move in means they reduce the radius, the speed of rotation increase. Okay, because the weight is actually being reduced.
1, 2, 3. One, 2, 3. Why is Ben Quaid always the first one in the middle? Are you guys going already?
Okay. So apa jawapan dia? Macam mana kita nak jadi? Kita tak nak terbabas dekat kes ni. What are the things that need to be changed? This one. This one. Okay. By reducing the radius of rotation, we are reducing the transfer of COG outside. So bila macam tadi contoh orang that like who hold the weight at, when they hold it far, what happen is the weight being distributed out means you need more force in order to sustain the same speed. But when you bring it near to the center, near to the axis, the weight is quite the means it means that it change the physics of the weight. Berat sama 10 Newton tapi 10 Newton keluar in rotation, it's going to be more than 10 Newton. When you bring it in, it will be 10 Newton. So when you have more weight, more force needed. Jadi you akan jadi lebih perlahan. Same goes as this this Formula 1 paradigm. Okay, if you are more from the outside and you try to have quite a wider curve, it is harder compare if you are on the out and you try to have a smaller curve. This one is going to be faster compared to the luar ni. Although the force being delivered is equal. Okay, kenapa? Pasal dekat sini weight become less since the radius is lesser. Dekat sini weight become more since the radius is longer. Okay, kalau kita tengok sini pula, kalau kita ada satu value kita bahagi dengan nombor yang lebih besar, you're going to get a smaller FC. Okay, contoh kan, kita ambil momentum atas ni 20 and then kita bagi dengan radius 2 meter, so your FC is going to be 10. Tapi kalau kita ada momentum of 20, the radius is 1.8. Berapa kita dapat? 20 bagi 1.8, smaller radius of rotation. Now we have 11, slightly more force, more centripetal force, resulting more velocity at the outcome. Ni cara permainan dia lah. Okay, so why centripetal force is important. Alright, so okay, now let's go to the moment of inertia. Moment of inertia ni weight, berat. Okay, moment of inertia ni adalah berat in angular motion. So in linear motion, when we talk of weight, mass, okay, kalau kotak ni 10 kg, you push this 10 kg ke mana pun, kg kat luar dah. Tolak ke sini, tolak ke bawah, still on a certain surface, the mass of this object will remain 10 kg. Will remain 10 kg. Okay. Tapi, pernah tak kamu rasa macam ni? Okay, kita buat dua condition. Siapa yang nak try, boleh try. Boleh berdiri. Okay, you berdiri. And I need you to stand up like this. Satu, angkat kaki macam ni je. Okay, yang kedua, saya nak you stand up macam ni. Angkat kaki macam ni. Okay, maksudnya satu ni quite lurus, satu lagi bengkok. And I need you to make a swing action. Okay, yang ini maintain the complex and try to swing. Okay, mungkin kita boleh buat yang ketiga. Kaki tu ni bengkok sikit kan. Nak buat kaki ketiga, kaki tu lurus je terus. And swing. Okay, first condition bengkok sikit. Second condition bengkok banyak. Third condition lurus terus. And I need you to report to me in sequence which is the lightest feeling. Okay, which feel the lightest, which feel moderate, and which feel the heaviest in these three condition. Okay, silakan. Lepas tu terus bagi saya jawapan.
3 je.
Tiga apa? Tiga apa? Tiga lightest ke heaviest ke apa?
Lighter.
Tiga lightest yang paling senang. Okay,
Bagi saya lah.
bagi kamu. Tiga lightest. Yang paling berat?
Yang bengkok habis.
Yang bengkok.
Nombor dua.
Okay, so tiga, satu,
Nombor 2.
dua. Macam ni lah.
Ya.
Okay. Alright. Sekarang saya nak kamu hayun. And then I need you to stop. Okay, I need you to stop. And determine which one is the most easiest to stop compared to others. Yang mana yang paling senang nak berhenti? Mana yang paling senang?
Kerana saya tak dapat lah rasa mana paling senang.
Cuba hayun kan, hayun. Satu, lepas tu ikut sikit hayun. Ikut banyak hayun. Bila kamu hayun tu, sekejap when you see me, saya nak kamu buat dan kamu rasa dia tau. Kan, katalah kita berdiri macam ni. Alamak, seluar saya sama. Okay, alamak, tak nampak. Okay, first tu, kamu bengkok macam ni and hayun dia macam ni. Okay, hayun dia macam ni. Okay, I need you to feel weight. I need you to feel the sensation of weight at the leg. Yang kedua, tadi satu dah bengkok kan. Yang kedua, buka sikit and then hayun dia. Hayun semua sekali. Jangan hayun sama je. So, hayun the whole section. I need you to feel the sense of weight. And the third one, just lurus je. Lepas tu hayun. Okay. Saya nak kamu rasa yang lurus ni dengan yang bengkok separuh, dengan yang bengkok terus, yang mana yang lagi ringan, yang mana yang lagi berat. Yang kawan kamu bagi tadi tu dia tak berapa accurate sebenarnya. It is not 3-2-3-3-1-2, no. Okay, kamu akan rasa this one yang paling ringan kali. Kamu akan rasa ringan. Okay, janganlah rasa the whole leg. You need to put You need to pick a place. Okay. Pick a week here. Means try to feel the week at the feet. Ni kan bahagian paling jauh. Okay. Dapat tak? Ke tak dapat rasa apa? So, kita orang dah hilang duri rasa. Something like that. Senyap pula tiba-tiba. Are you there? Are you still there? Kamu masih ada
Ada
di
sir.
sana?
Yang berat yang angkat nombor 2 kot.
Ya. Kamu rasa berat angkat. Saya nak kamu rasa berat goyang. Berat angkat for sure lah because you contract your muscle here. Saya nak kamu rasa berat goyang. Okay. Concept is this. This is the concept. Tangkap betul. If we have linear weight, okay, 10 kg, dekat mana pun, it will be 10 kg. It won't change. Okay, it won't change. But, when we have condition like this, satu, this is where the weight being being centered. Dua, this is where the weight being centered. And tiga, this is where the weight being centered. The weight of this region, dia tak berubah tau. Katalah kaki kamu ni kan. Kaki kamu ni, feet kamu ni, let's say 5 kg lah. It will remain 5 kg, that's true. But, when we go for rotational action, okay, when we go for rotational action, the weight differ. Jadi, in order for us to determine the weight, we are going to use formula of moment of inertia, I. Bila dalam angular ni kan, nanti kalau kamu baca buku ke apa, kamu akan selalu jumpa moment of force, moment of inertia. When you see moment of angular cases. Okay, angular cases. Means, kalau moment of inertia, moment of inertia. Inertia ni is actually weight. Okay, weight. Dekat dalam linear. So, moment of inertia, we try to find, weight pula. It talks about mass. It talks about mass. Okay, when we talk about moment of inertia, means we still talk about moment, but mass. Moment of ni, nampak je ni, angular. Angular mass. Jadi, formula dia I equals to mr square. Sometime kamu akan nampak mk square. Beza dia satu je. Ni radius. Radius of rotation. Ini radius. Radius of gyration. Most of human is mk square because our radius keep on changing. Okay, the center of mass keep on changing based on kita punya kita punya condition. Tapi kalau kita ada satu benda, katalah pembaris. Ni dia punya radius. Radius dia berubah tak? Kalau kita letak pembaris ni macam ni, kalau kita letak pembaris ni macam ni, kalau kita letak pembaris ni macam ni, my question is simple. R ni berubah tak? R1, R2 ni ini kamu bayangkanlah. R1, R2, R3 ni sama ke berubah if the pembaris is sama? Does this change?
No, sir.
No. Tapi kalau kaki kita, katalah kaki kita ni sepanjang 1 meter. Kalau macam ni, semeter tak? Kalau macam ni, semeter tak? Kalau macam ni, semeter tak? Katalah yang ini 1 meter. R dia. Kalau yang ini, is it semeter? From axis of rotation to the point of application, ya macam ni. Ni kita assume lah semeter. Kalau yang ini, daripada axis of rotation sampai point of application, semeter tak? Kalau yang ini, axis, point of application, semeter tak? Yang kedua, ada semeter. Kalau yang ini semeter, yang ini ada semeter tak? Ha, cuba jawab. Kalau kata saya bagi nombor A, B, C. If the length of C is 1 meter radius, length of B dengan A, is it 1 meter? Or is it less than 1 meter? Yang mana satu? Semeter ke tak sampai semeter? Ni assumption. Kalau C ni 1 meter, A dengan B?
Less.
Less. Jadi maksudnya, in human motion, most of the time, our joint angle, our joint, the length of joint keep changing. Okay, the length, it depends, the length is equal, but the distribution of weight keep changing. It depends on the shape. So kita akan pakai, instead of R, we are going to use K, radius of gyration. Okay. Now let's take a look. These three feet, okay, these 3 feet A, B, and C is 5 kg in mass. However, when we start rotating the feet, it change. Okay, katalah yang ini 45 cm. Yang ini 70 cm. Okay, so 0.7 meter, 0.45 meter. Now, when we start swinging the leg, means that when the leg column start to undergo what we call it, angular motion, the weight of the column is going to change. The weight of the system, the mass of the system is going to change. And in order to measure the mass, we are going to conduct measurement for moment of inertia. Let's measure moment of inertia for A first. So I A equals to mk square equals to 0.45 square. Okay, yang ini IB equals to 0.7 square, and this one IC equals to 1 square. Apa kita dapat kat sini? 0.45 square kali 5, 1.01 kg. Okay, nombor 2 pula, 0.7 square kali 5, 2.45 kg. And number 3 will be 5 kg. Okay, 1 square kali 5. Nampak? We have 3 different placement of leg, the same weight of leg and the same mass of the leg. However, during angular rotation, the weight change. If the radius is less, the weight is going to be lesser. If the radius is long, the weight is going to be heavier. Ni yang terjadi tadi tu. Jadi macam mana kita nak dapatkan apa ni? Kita nak dapatkan curve yang cantik. How we want to manipulate the centripetal force in rotation. Why cikgu tadi tu can rotate faster when they put the weight near to the body rather than out of the body. And this is the reason why. Because weight in rotation change in nature. Okay, it change in nature. The longer the distance between the weight and the axis, the heavier it become until it is solid weight lah. Kalau dia 10 kg sampai 10 kg lah dia boleh pergi, dia tak boleh lah pergi extra than that. Is it? Soalan dia. Is it? Yes, it can go more than that. Habis kalau radius of rotation dia besar, let's say radius of rotation dia 2 meter. Radius of rotation 2 meter. So we have ID equals to 5 times 2 square equals to 20. 2 kali 2, 4 kg. 4. The original weight of the system is only 5. But if it is being put 2 meter from the radius of rotation, what is going to happen is the weight of that rotational system, instead of 5, now it become 20 kg. Sedangkan kaki tadi 5 kg je. Ni nampak permainan radius of rotation. And this is the reason why in rotational, the linear weight can change accordingly to the distance between the weight and the axis of that rotation. Ni dia. Okay, dapat? Itu adalah moment of inertia. Banyak pula. Okay, that is moment of inertia. Inertial properties for rotating bodies represent resistance to angular acceleration based on both mass and the distance of the mass distributed from the axis. Ni contoh. Jadi kalau kata kita buat kajian dengan benda-benda yang pegun, okay, object that does not change in term of shape, we are going to use radius of rotation. But if our analysis using body part that able to change, nampak macam ni. Those two is actually the same leg. Okay, it is the same leg. Tapi the first configuration is bending, the second configuration is standing straight. So if we compare the mass or the moment of inertia for A compared to moment of inertia for B, moment of inertia for B is going to be more. Means that this leg is going to when being rotated is going to have more weight, more mass compared to condition A. Why? Because condition A radius dia pendek. Jadi radius ni daripada mana ke mana? Daripada axis ke center of mass. Dia ambil center of mass, center of paha, center of lower leg, center of feet. Same goes here. Center of paha, center of lower leg, center of feet. Tu dia punya mass lah. Okay. The center, the COG for every part represent the mass for that particular part. Okay. Sampai sini dulu ada soalan. Jadi kalau kita tengok dalam dua ni, dalam condition A dengan dalam condition B, which condition is much easier for you to swing? A or B? Based on the information that you already know. A or B, which condition is actually much easier for you to swing? Yang ini kah? Or yang ini kah? Mari kita nak. A. Okay, A. Pasal dah terang lah kalau radius of gyration dia pendek, weight dia jadi sikit. So, dia lagi mudah. Tapi kenapa tadi ada orang rasa dia susah? Okay. Pasal they are not swinging the whole leg. Okay, they are contracting just a muscle here. So, dia bukan swing, dia just contract, retract, contract, retract. Jadi, bila kita masuk tiga-tiga, tiga-tiga rasa lebih kurang. Yang mana satu lagi berat. You unable to feel the weight. Okay. Right. Okay, kita tengok contoh. Okay, we go to examples. Alright, we have a racket. Let's say racket, and this racket mass is 1.1 kg. Okay, 1.1 kg racket has a moment of inertia about a grip axis of rotation. Okay, jadi dia punya I is 0.4 kgm squared. Okay, ni moment of inertia ni. Maksudnya, when people swing this racket, the sense of weight for this racket is just 0.4. It is not 1.1. Soalan dia, what is the radius of gyration ataupun radius of rotation? Okay, berapakah radius ni? Ni bukan yang ni, sorry, this is not it. Mesti ada tangan orang yang pegang kan. So what is the radius of gyration from weight, point of weight being distributed to shoulder, axis of rotation? What are the R ataupun K? Okay lah formula tadi. I equals to mk square. So I 0.4 equals to 1.1 K square. So K is 0.4 divide with 1.1 square. Berapa kita dapat? Ha, 0.6 meter. So ni jarak dia ni 60 cm. So mungkin action tu dia bengkok lah macam ni. Dekat-dekat shoulder, dekat head. 60 cm. Ini cara kita guna dia. Okay. Dia kejap. Player angular velocity. Angular velocity kau. Apa soalan ni? Moment of inertia standing arm. What is the average radius? Confusing. Okay. Contoh lagi satu. Kita ada player volleyball. Player volleyball. Tangan ni bahu dia. So tangan player volleyball nak spike 1, 2, 3, 4, 5. Okay. This region of arm, the mass is 3.7 kg. Okay, and it moved at an average angular velocity. So the hand move at an angular velocity of 15 radian. Sorry. Okay, kalau cerita angular velocity, it is not here. It is here at the joint. 15 radian per second. Okay, during execution of the spike, if the average moment of inertia, okay, if during this action, during the spiking action ni, the moment of inertia of this hand is 0.45 kgm square. The question is, what is the radius of gyration daripada center of weight to axis of rotation? Berapa dia punya radius of gyration or radius of rotation arah teki? So we go with this similar equation. I equals to mk square. 0.45 equals to 3.7 ni kena tukar dulu. This one is in sorry, betul lah math. Mabuk dah saya. 3.7, sorry, mabuk. K square. Jadi K ialah 0.45 divide with 3.7 square root of it. Apa dapat? Kosong point 37 meter ataupun 37 sentimeter. Ni cara untuk kita pakai moment of inertia or weight. Okay, so by here you know that when our body part or when anything undergo an angular motion, the weight is going to change. Kotak 10 kilo. Lepas tu kita rotate dia hayun, masa kita rotate, that 10 kilo change according to radius. Okay, the longer the radius, the heavier the weight is going to be. The shorter the radius, the lighter the weight is going to be. Tu adalah moment of inertia ataupun mass in angular acceleration. In angular. Okay, mass in angular. It's known as moment of inertia. Okay. Next. Sekejap minggu depan cuti kan? Kita cover satu lagi je lah. Sekejap saya nak tengok kita dah sampai mana. We actually have covered things quite fast. Kita sekarang dekat week 8. Angular kinematics ni kita dah cover betul? Is it? Yes, angular kinematic kita dah cover. This one is mana? Week 8, week 8. Okay. Week 9 dengan week 10 ni more towards how to conduct analysis. So sekarang kita dah cover yang ini. Week 11, week 12. Okay. So we try to cover another one which is angular momentum. And then we are going to stop. Okay. So angular momentum is quite similar as linear momentum. Sama je. Kalau tak percaya tengok sini. Linear momentum, we put it as m equals to mv. Angular momentum, dia ialah h. M ni mass. Jadi mass dekat dalam angular tadi kita dah belajar ialah moment of inertia. While v is velocity, dalam angular, velocity ialah omega. Inilah angular momentum. Or it can be written as I ni, kita boleh kembangkan tadi kepada mk square. And then omega. These two things is equal. Okay, these two things is angular momentum. Okay, angular momentum is the amount of movement happen to be in angular. Kalau angular as a linear momentum, kita tengok linearly angular, benda yang berpusing, berapa angular momentum dia. Okay, so under angular momentum, the concept that is quite important is actually principle of conservation in term of angular momentum. Ini yang paling penting. Okay, pasal like what we have learned from the beginning, centripetal force and whatsoever, when we talk about angular motion, we try to have a motion that is quite fluid. Macam ni. Kita tak nak motion yang macam ni. Kita tak nak motion yang melunjung macam ni. Kita nak motion yang fluid. Means kalau motion yang fluid ni, force being delivered at any given point of the rotation is equal. Acceleration, both tangent and radial, with centripetal force, the amount will be equal along the way. Same goes as momentum. Kalau momentum satu tempat tu tak sama dengan tempat yang lagi satu, contoh kan kita ambil ni, sukan ni. Sekejap we go to this spot. Angular momentum play a major role in this kind of sport that require a lot of movement.
This Philippine diving team was formed at the last minute, and this is the hilarious result.
Okay, angular momentum ada berapa bahagian? Mass dengan apa lagi satu? Kita ada moment of inertia dengan Ome1. Come on guys.
Omega.
Omega. Okay. Jadi dalam setiap putaran ni, tengok saya akan tunjuk satu-satu Oh, laju pula dia terus pergi. Okay, ni kan. How we want to slow it down. Slow down. 0.5. Okay. Okay. In diving, we can divide this action into several phases. Such as, kita ambil yang ini pertama, jump off. And then, kita ada tucking. Okay, tucking process. And then sepatutnya selepas tucking ni dia akan ada release lah. Release and enter. Okay, tapi Mamat ni tak ada. Lepas tu enter dia. Okay, that is the enter. For every single action dekat sini, notice one thing. Okay, I need you to notice one thing. First, saya nak kamu notice distance. Okay, distance COG dia between axis of rotation dengan weight. Katalah kita ambil weight dekat dada. Okay, kita ambil weight dekat kaki lah. Weight dekat kaki. So, I need you to observe, one, distance between kaki and COG. Two, the speed of rotation. Okay, jadi distance ni tadi is going to cover the moment of inertia. And the speed of rotation that is going to cover the omega. So, in order to get a good diving, every single phase, these two is going to equalize with one another. Contoh, kalau macam fasa ni dia punya moment of inertia dia besar ke kecil? Ni radius gyration dah kecil, so moment of inertia dia besar ke kecil compare dengan fasa jumping tadi. Jumping is A, tucking is B, moment of inertia mana yang lagi besar? Come on. Which moment of inertia is larger? Jumping ke tucking? Tak payah sakit kepala. Yang mana radius gyration pendek, dia lagi ringan. Maksudnya moment of inertia dia kecil bila radius of gyration dia pendek. So masa ni, moment of inertia dia kecil. And you're going to notice, bila moment of inertia dia kecil, rotation dia laju, means there are rotation. Compare to fasa yang ini. Okay, fasa yang ini, moment of inertia dia besar, but lacking of rotation. And now, moment of inertia dia kecil, now dia ada speed, dia ada momentum, dia ada rotation. Supposedly, bila dia cuba untuk untuk go to the last phase, which is dive, dia kena kembali pada fasa yang pertama, which is moment of inertia besar and rotation dia kecil, omega dia kecil. However, he failed to do so. Kenapa? Pasal dekat sini dia dah perlahan. Okay, dekat sini omega dia dah tak ada. So, bila omega dah tak ada, momentum dah tak ada, dah tak sama. Jadi pergerakan tadi dia jadi pergerakan yang it's not fluent. It's going to be kaput. Macam tu. Kejap lagi kita provekan by equation. Cepat. Gila bunuh diri. Okay. So, in angular momentum, it is actually quite similar as linear momentum where we have principle of momentum conservation. Sama je ni. Okay. So, especially in that kind of action, all of this, kita ada fasa 1, 2, 3, 4, 5, the amount of momentum is going to be equalized. So, I'm going to show you 2 or 3 phase and you're going to get the idea. Kita ambil ni fasa 1, 2, 3. Okay. We are going to name the phase as fasa 1, phase 1, jump. Phase 2, tuck. Phase 3, rotate. Okay. So, let's now assume kita ambil berat kaki. Okay. Let's assume berat kaki ni berapa? 15 kg. So, the mass is 15 kg. Now, kita ambil R1, R2, R3 ataupun K lah. K1, K2, K3. Radius. The radius is from the middle of the leg to the COG. Okay. Katalah radius yang ini kita ambil 1 meter. Ni fasa 1. Okay. Equals to 1 meter. Fasa 2. Okay. Dalam proses tucking ni, kita jadi daripada tengah ni ke COG, we assume that one is around 0.6 meter and last one is 0.3 meter, 30 centimeter. Okay. Now, okay, kita cuba cari berapa dia punya momentum here. Okay. We know that momentum H equals to mk square omega. Kita belum ada omega. Okay, kita ambil satu dulu. Dekat sini. Okay, katalah momentum dekat sini, it is just a small momentum. Maybe dia punya omega 1 equals to 1 radian per second. 1 radian per second. Okay. So, kita cari dulu berapa angular momentum satu. M will be 15. The K will be 1 square 1. Jadi kita dapat kat sini 15. Apa tu? Apa unit dia? What is the unit for angular momentum? kg m square s. Kg ni m. Okay. M square ni K. Okay, M. Okay, M1 je. Lagi satu M datang kat sini. Okay, ni pun ada MS kan, omega. So, 1 kg M square S. Okay, 15. Now, when you know one momentum, the other momentum, H2 and H3 also will be 15. Tapi kita punya ni berubah. Nampak? So, bila benda ni berubah, automatically omega 2 and omega 3 is also going to change. Now, let's try to find out. Okay, kita ambil H2. H2 equals to 15 0.6 square omega. Try to find the omega. So, now we have 15 here. Okay, berapa kita dapat kat sini? 0.6 square, 0.36 sama dengan 15 0.36. Ni 15 okay, omega. Cuba selesaikan. 0.36 kali 15 kita dapat 5.4. 5.4 omega sama dengan 15. Omega sama dengan 15 over 5.4. We have 37.5. Okay, nampak? Dah berubah. Meter pula. Omega dalam apa? Omega. Angular velocity, radian per second. Betul tak? Is it true? Okay, and then we have H3 equals to 15. Now, dia punya radius of gyration lagi pendek. Square omega. H3 is 15 equals to 15. 0.3, 0.3, 0.9. Is it? Wah, ni senyap sepi. 0.09. Okay, salah. 0.3. 0.09. Omega. So 0.09 times with 15, we have 1.35. 1.35 omega equals to 15. Omega equals to 15 over 1.35. Tak ada. Eh, 15. Betul lah, 15 bahagi 1.35. 11. 15 bahagi 5.4. Betul lah, macam salah. 2.77. Lebih. 2.77. Okay, nampak ada 3 benda beza. Okay, saya pindahkan kat sebelah. H1, okay, momentum 15. Omega 1, 1. H2, 15. Omega 2, 2.77. H3, still 15. Omega 3, 11.11. Okay. Omega represent how fast it rotate. So here, we know that omega 1 is 1 dekat sini. Maksudnya, rotation dia kurang. Jadi, nak counter dengan rotation yang kurang, radius of gyration dia besar. Masuk dekat H2, rotation dia increase 2.77. Maksudnya, dia lagi laju. To counter that, the radius of gyration shorter. Compare to yang ketiga, lagi laju daripada yang kedua dan yang pertama. Okay, cuma along the process, all of these 5 P's, the amount of angular momentum is going to be similar. That does not going to change. Sama semuanya, takkan berubah. Ini principle of angular momentum. Although at any given phases of action, the angular momentum is going to be similar. And then only you are going to get a fluent action. Or else, kamu akan dapat benda-benda macam ni. Ni bila angular momentum tak sama dekat setiap fasa. The phase that they should have a good rotation, dia tak rotate. The phase where they need to have a good a longer center of gyration with a slower rotation, dia tak ada. Rotation dia masih lagi laju. Macam tu. Jadi kalau this angular momentum does not be conserved throughout the phases, what is going to happen is the action is not going to be fluid. It's going to be jagged. Dia tak dapat lah benda yang hasil apa yang dia nak tu. Because rotation dia tak cukup laju dekat atas tadi. So, dia tak habis mesin. How to overcome this one? They need to have
This type
a
of
much
competition
faster
is different to any you've seen before, and the goal is to go out into a horizontal hover with arms and legs extended in an X formation until they hit the water, which is very painful.
It's going to be cool to see what he can do, if he can go higher in top 5. Doesn't have the control in the air, it seems that's like...
Yang ini terus tak ada angular velocity dia terus out of order. Pasal dia tak cukup untuk dapatkan rotation.
Stop gaming.
Okay, so that is actually angular momentum, the interrelation between mass or moment of inertia with omega. So they are going to counter with one another in order to get a good rotation or a slower rotation in a certain phases of action. Itu adalah angular momentum and principle of angular momentum conservation. Cara lain dia kalau kita nak tengok angular momentum is by subtract lah. Okay, kita minuskan angular impulse 1 dengan angular impulse 2. Ni angular impulse. Okay, so angular impulse kita pakai moment of inertia again, moment of inertia dengan omega. Sama je. Ni momentum lah. So angular impulse is momentum 2 minus momentum 1. Momentum final minus momentum initial. So you are going to get impulse in between. Okay. So I'm going to stop here. Okay, angular momentum ni saya akan berhenti dekat angular angular impulse. Okay, kita ada dua je lagi, angular impulse dengan torque. Yang ni saya dah cover belum dekat topik sebelum-sebelum ni? Impact, perfect plastic dengan perfect elastic.